All right, so let's see. This is the section 2 of the energy test review solutions here. 0.5 kilogram cart released from rest on a smooth incline has a gravitational energy of 6 joules relative to its base of the incline. So here, calculate the speed at the bottom of the incline. Oh, that's easy. So if you want to see the picture of this, it should look something like this. Okay. So it says it has a gravitational energy of 6 joules. So energy 1 is going to be equal to energy 2. Okay, energy 1 is just your mgh. And that's basically your potential energy. It's going to be equal to your kinetic energy. And you know that is going to be 6 joules. They just give it to you. And that's going to be equal to the speed of the object. So it's going to be 1 half mv squared. So you know that as what's the speed of the bottom? So let's work out some math. So it's going to be 2 times 6 divided by m is going to be equal to v square root that. That should get you out of the squared term right there. Okay. So 6 times 2 divided by the mass, which is 0.5. So velocity here is going to be 24. Okay. When the cart has rolled halfway down the incline, the gravitational energy will be what? I think it would be less, right? So hold on. Oh, no, this doesn't look right. Give me a second. So 6, gravitational energy 6. Multiply that by 2. Divide that by its mass. Yep, 24. I gotta square root the 24. I'm sorry. Yep, I forgot to square root the 24 because I'm like, the velocity can't be 24. So velocity was equal to 4.9 meters per second. So this is 4.9 meters per second. Okay. When the car is halfway, the gravitational energy would be what? Well, if you think about it, here it has 6 joules of energy. Here it has 0 joules of energy. And if you look like the formula, U is equal to mgh. Notice this is a linear equation, so it's declining at the same rate. So here, when it is half, okay, it would just be half this. So it would just be 1 half mg squared at half. So this should be 3 joules. Likewise, if it's like, 1/6 on its way down, right? So this is like 1/6 on the way down, it'll be 1 joule of energy, right? 2/6 down, it'll be 2 joules of energy. 3 at the middle, 4 joules, fourth way down, and 5 out of 6 would be 5 joules of energy down here. Okay, so it would be less than 3 joules of energy. That is the reason why. Again, it's linear. Okay, so it is when the cart has rolled halfway down the incline, the kinetic energy will be what? Well, you could work out the math, but at the top or your initial, right? It had 6 joules, right? Then, right? This is all kinetic. This is all potential, right? Halfway, it has both potential and kinetic. And in the end, it just has all kinetic. Okay, so we know at the end it has 6 joules of all kinetics. Here, it's probably 3 plus 3. Okay, because it is halfway through. Okay, so 6 joules of energy plus 3 joules of energy. This is just energy. You don't know what its velocity is, but you know that the kinetic energy must be 3 joules for kinetic and 3 joules for potential. Okay, so it is equal to 3 joules of energy. When the cart has rolled halfway down the incline, the cart of the speed will be what? Well, we know it's 3 joules of energy, and that has to be equal to 1/2 mv squared, right? And so um, halfway of it so its speed will be what? Do I have its mass? Well, I do have. I have 0.5 kilograms. So let's see if I can do that. Becomes 6. What's the mass? 0.5. So what I'm doing is I multiply this by 2, then I divide it by the m. Okay, to get me v squared. So v is going to be 2 times 3 divided by 0.5. So 2 times 3, divide this by 0.5, square root 12, square root 12. So I got velocity is just equal to 3.46. So I know the bottom is 4.9. Okay, the right here, it is half of its speed at the bottom. Wait, hold on. It wouldn't be half. It's not half. It's not half. It can't be half. Look, it's not half. Half would be like what? 2.45. It can't be greater than the speed at the bottom. But it is less. We know it is less. The reason why it can't be half because you see the square root term here, or the square term. That's why. A 1.4 kilogram car is released from the top of the incline. At the bottom, it will be what? Well, you double the mass. If you double the mass, what happens when you double the mass? No. It would be the same. It would be the same speed as the cart, right? It wouldn't change. Okay, the energy is the same. Okay, notice the mass at the the mass cancels out in the conservation of energy equation, right? So the speed will be the same. Yeah. Let's look at this one. A stone is sitting on top of a compressed spring. It is sitting at a compressed. The potential energy stored in the spring earth stone is 40 joules. Let me just draw this rock. Let's see. Here's your rock. Stone is on top of a compress. So this is kilogram, 1 kilogram mass, potential energy. So U is equal to 40 joules. I know U is equal to 1/2 kx squared. I'm just gonna write that because I feel like I'm gonna forget it. The spring is released. The spring is released. Thrown the stone upward in the air. How much kinetic energy? Oh, that's easy. So it goes from the potential energy of the spring is going to be equal to the kinetic energy of the stone. Okay, this is initial, this is final. So it's 1/2 kx squared is going to be equal to the kinetic energy. So 1/2 m v squared. The halves cancel out, so that looks like that. Mv squared. I want to know what? How much energy would the stone? Oh, no. I don't even need velocity, bro. No. Psh. I don't even need velocity. I know that it has to be 40 joules, right? Because the energy has to be converted, right? If it's 40 here, if this is 40 joules here, it has to be equal to 40 joules here. So it's 40 joules. How much gravitational energy relative to the spot where the stone was released will the stone have when it reaches its peak? Ah, here is going to be converted. So this one would be U of S is going to be U to G, right? I'm ignoring kinetic energy. So this is what? 1/2 kx squared is equal to mgh. All right. How much? So this is what I have. What? 40 joules here is equal to mgh. So I need to know what? How much gravitational energy relative to a spot will it have at its peak? Again, at its peak, it should be again at it reaches its peak, right? Maximum height. So this is at max height. It should still be 40 joules of energy. Okay. because it's all getting converted. Calculate the height above the release point which the stone travels. Oh, that's this math here. I was trying to do some math here. Do I know the mass of the stone? Do I know gravity? Yeah, so it's 40 divided by mg is equal to the height. Just could do that math right there. 40 divided by m 0 0.1 times g 10. Yep. So I got height is equal to 40 meters. Suggests something we could change about the situation that would cause the stone to reach a height double its calculation in part C. How do we get 80? How do we get 80? Basically, they basically said height becomes 80. So this is mass, gravity, height. They want this to be 80. Okay, we have 1/2 kx squared, right? So mass goes away. Okay, so mass goes away. You can change the spring. Well, the 1/2 goes away because the half the math the mass doesn't change. The 1/2 goes away. So you could do a couple of things. If you want this to be, if you want to double this, so you can, and you can double this, so you can. So one option is to double the spring constant, right? This goes up by 2, so this has to go up by 2. Okay, 2. You could decrease, so you can cut G in half, right? This goes down, so this has to go up, right, to get you the same value. Or you can do something to X, but it's gonna be weird. You can if you like square root it, but there's still some more math. So double the K or cut the G in half. Those are your most common ones. You really can't cut G in half, right? Unless you put it on a different planet. So the best answer would to just be doubling the K. Okay, so there you go. All right, that would be just the best way. Okay. There's other way things you can do, but like the velocity, ugh, I'll ignore that because of the square term. Let's look at this. Oh, oh, haha. A laboratory motion detector records the speed of a car as a function of time. Stop at rest when the car is 50 centimeters. Ugh, why do you do that? Let's just convert this. 0.15 meters. 0.15 meters. Car is initially released from rest. The kinetic energy of the car at the line mark on the track is equal to the gravitational energy of h. So this is, there's a height here. On the preceding diagram, draw and label the distance you would measure from the height of the car. Oh, haha. Wait, wait. I'm sorry. Wait. Oh, this shouldn't be the height. Because if you look, I gotta draw it straight here. If you look, this is where the detector was. So if you make it straight, the proper height should be this. Okay. Uh, on precision draw and label the distance you would, yeah, this would be the height you would have to measure for the height of the car. Yeah, this would be the height. Line mark on track is in front of centimeters. Okay. Yeah, that's fine. Explain in some detail how commonly available laboratory equipment could be used to measure and label the height. Explain in some detail how commonly available lab equipment could be used to measure the height. In a laboratory, motion detector records the speed of a car as a function of time, stopped as it reads when the car is in front of the detector. A ruler? I mean, you could do a ruler or a laser tape. Right? meter stick. Okay. Then you would also use a you could also use a protractor if you need the theta for the angle, but you shouldn't. Okay, then you could work out some trig if you would like for the height. Okay, because again, if this is theta, if you could measure theta here, you can get height by using sine of theta is going to be height over the ramp amount, which is 0.15 meters. So again, if you can get theta, you can get the height. So you could also use a protractor to get the height. If the height h was double in a second trial, the motion detector would read, well, if you double the height, that means if you double the height, hold on, let's think about it. mgh is going to be equal to 1/2 mv squared in the end. If you double the height, the energy is doubled, right? So what happens to the speed? Masses goes away. Masses goes away. The 1/2 goes away because we're comparing it, right? So g goes away. So height is just v squared. Okay. So if I double the height, so double the height. What happens to the velocity? Double the height. What happens to velocity? Square that. Velocity is the square root 2 of some height. Let's see. So it would be, yeah, right here. Work it out. The square root of 2 times the speed of the first trial, right? Because this would be the new velocity, would be a square root 2 times the height. So there you go. 4. A student A lift a 50 Newton box off a floor. Uh, ooh, that's weight. Ooh, that's force of gravity. That's interesting. Force of gravity was equal to 50 newtons. Height was equal to 0.04 meters because again, this is converted. This is centimeters, so it has to be converted to meters. 2 seconds. Ooh, time is 2 seconds. Ooh, there might be a power. Student lift. So this is student A, and student B lifts a 40 Newton box. So force gravity is equal to 40 newtons here. Do not put mass. Okay, it's newtons, force of gravity. And that goes up to a height of what? 0.5 meters, and the time is equal to 1 second. Okay, I'm just going to put this into mass, okay? So this is equivalently to 5 kilograms, because I'm just dividing this by 10 g. This is equivalently to 4 kilograms. Again, right? 40 newtons is equal to mg. Okay, I know that uh, g is 10. So you see how the mass was equal to 4. Okay, just converting it. All right. So same work, but develop more power. What? No. That makes that is very interesting. Okay, how much work did student do? Okay, you could answer it different ways, but I think student A. Let me bring this down. There's a lot of ways to answer this. This is very interesting. Okay, so how much work? You could do it in many ways, but for me, I'm just going to do work is going to be change of U, right? It had 0 minus mgh. Okay, I have m, I have g, I have h. Okay, so first student was I have 5 times g, 10 times height, which is 0.04. So this is 2. Right? I understand there's a minus. Okay, I understand there's a minus. Okay, if you want to be really picky, but I'm going to take the magnitude of work. Okay, Jesus. Okay, same thing here. 0 minus mgh. So, okay, this is going to be what? M, which is 4 times 10, and it lifts it to 0.5. So 0.5. So this is 2 joules. Yeah, of work. All right, so same amount of work. More work? Nope. Less work? Nope. More, same amount of work. What about power? We know power is defined by work divided by is work divided by time. So time. So power is equal to work divided by time. So this becomes 2 over 2. This becomes 1. Okay, watt. This would be power equals to work over time, which is equal to what in this case? 2 divided by, in 1 second, 1. So here it was 2 watt. Student A, it has less power. Okay. The reason why it's less power is because he did it in a longer time. Okay. Why? Student took more time. Compare A instead lifting a 40 instead. Now student A instead lifts the 40 Newton box from the floor diagonally, moving the 40 centimeters to the right and 40 centimeters up in 2 seconds. What up? So this is the first scenario that he did. He went 50 newtons up the first time, right? In this case, he went instead lifts the 50 newtons. Instead, he moves the 40. So he moves it 0.04 meters to the right. Then he goes up, right, 0.04 meters, and that took him time. Time is still equal to 2 seconds. Compare the work he did originally. Compare the work. So the work here is just mgh. Again, energy is the potential energy. So here, energy is just minus mgh. Okay, or plus mgh. You just take the magnitude, whatever. Here, he moved it up the 50 Newton box with a 50 newtons box. So it took him how much? 2 joules. So it took him 2 joules here. So here, it also took him the same amount of joules. Okay. All right. Compare the power he developed originally. Does student A develop more or less power? Um. So, does distance change power? No. Right? Does this no because it's the same amount of time. So compare the power. It's the same time. So divide this by 2 seconds. Right? Power is gonna be still equal to 1 watt. Divide this by 2 seconds. Power is still gonna be equal to watt. So it's the same time. So same power. Again, the distance doesn't matter. Okay, there you go. Oh, wow. That video was easy to make.